Hello everyone, my name is Anastasia and I'm here with my friend Gladys. Today, we are going to share our research titled Real or Fake Job Posting Prediction using Random Forest, Long Short-Term Memory, and Multinomial Naive Bayes. So let's begin. Technology rapid development and change society, transforming many aspects of life. This includes the process of looking for employment, where job seekers now can use social media, job seeking application, and job sites to look for a job. The opportunity of online job posting makes scammers come up with many ways to disguise their practice, such as basic, generic, and simple requirement, uncommon recruitment process, and even asking for personal details that there is nothing to do with the recruitment. So, research is conducted to detect fake job posting to prevent fraud from happening by using machine learning and text mining based technology, which is commonly used in fraud detection due to its ability to analyze and identify patterns and perform anomaly detection. The problem statements are: first, how to build a machine learning or deep learning model that can accurately detect online fake job posting, and which model gives superior performance between random forest, long short-term memory, and multinomial naive Bayes. The second problem is what job factor can be used as consideration to build an accurate fake job posting model. Next is the objective of the research. First is to build a model that can accurately detect fake online job posting with machine learning and text mining as its basis. Second is to identify and determine key features that affect the data most, then analyze further based on the key features. Third is to evaluate each model performance and compare them based on the evaluation metrics, such as accuracy, precision, recall, and F1 score. Next is the methodology we use in this research. This research will go through 6 major steps, begin with data collection, and then exploratory data analysis, then preprocessing. After that, the data will be split into 80% of training and 20% of testing. The training data then will be used to train the model, and then all the model will be evaluated and then tuned. If the result is optimized or if the result is like what we want, then it will end the process. Here are the details of our methodology. The first step is data collection and description. The data we use for this study is taken from Kaggle titled Real or Fake Job Posting Prediction that contain 18,000 rows and 18 features. The dataset is heavily imbalanced, with 866 rows fraud data and 17,880 non-fraud data. For the modeling process, only 4 text columns are selected. Those are title, company profile, description, and requirement. After we're done with some visualization using graph and so on, we can conclude that fraud job postings are mostly full-time employment and don't specify required experience, education, job function, nor industry. The second step is data preprocessing. The data is cut down to 10,000. Well, all fraud data is included and non-fraud data is taken by stratifying employment type. Then the data went through cleansing, where we remove punctuation, symbols, and converting the data into lowercase, followed by tokenization and stopword removal. Lastly, we do stemming, lemmatization, and oversampling methods like smooth, ROS, and other sign. The next will be continued by my friend Gladys.
Next, we split the data into an 80 to 20 ratio for train and test sets and apply 2 text representation methods, TF-IDF for the machine learning models and word-to-fact skipgram for deep learning. So we're comparing the results of TF-IDF paired with machine learning versus word-to-fact paired with deep learning. We then experimented with resampling, whether or not to use resampling techniques and which techniques to use. We used ASIN, Smooth, and ROS, and also tuned the model's hyperparameters with grid search. We evaluated all models' performances based on regular classification performance metrics, which are accuracy, precision, recall, and F1 score, although we focused more on accuracy and F1 score. Here we have the performance comparison between models. The random forest model performed with 0.96 accuracy and above 0.8 in F1 score. The model, trained with data resampled by Edison in particular, performed the best with a 0.87 F1 score. Multinomial naive Bayes and LSTM, however, resulted in only 0.61 and 0.48 F1 scores respectively, despite the high accuracy scores seen over here. Now onto the key findings. Here we have the best performing models sorted by accuracy and F1 score, along with the resampling techniques used. The random forest model performed the best and it has the highest scores across all metrics overall. The model with data resampled using Edison resampling resulted in a 0.87 F1 score, meaning that its ability to detect fraud and to detect it correctly despite the little amount of fraud data is quite high. Both multinomial naive Bayes and LSTM seem to struggle with identifying fraud considering the highly imbalanced class ratio, where as you can see here, the F1 score is only 0.61 and 0.48. From this experiment, we managed to gather that whether or not resampling was used heavily impacted model performance. The machine learning models managed to detect fraud better with resampling, considering the F1 scores, though the same can't be said for LCM, since its performance metrics showed the same results across all fields. We've tried several architectures for LSTM, and none have given significantly good results. But we've learned that for this specific dataset, the simpler the model, the better. In LSTM, for instance, more complex architecture doesn't equate to significantly better performance, whereas simpler architecture converges faster. The LSTM model resulted in better scores during training when resampling wasn't used, indicating that the resampling techniques might be confusing for this model. Unfortunately, the test results were the same as seen in previous slides, and thus there's no telling whether there was overfitting. The reason why the multinomial naive Bayes model wasn't able to predict fraud well might be due to the fact that it works better with small vocabulary size, whereas our data has nearly 80,000 words in total. Our conclusion from this research is that simple machine learning models were able to learn better despite class imbalance, and that the job title, company profile, description, and requirements of a job posting contributes a lot in determining whether it's a fraud posting or not. For future works, adding more data can be considered, such as using the whole 18,000 rows from this dataset and maybe adding other datasets into the mix, giving the models more to learn from. Other features can also be considered to use for training, since in this case we only used 4 of them. That is all for our research presentation. Thank you for your attention.